Welcome everyone to first colloquium of EF. Today, the first speaker is Antonio de Felice. He is an associate professor at Yukawa Institute for Theoretical Physics in Japan. His expert is just about cosmology and modified gravity theory. And then today he will talk on minimal theory and modified gravity models. This is a hot topic about gravity theory nowadays. Moreover, Antonio is just like our own friend for us because he was worked here before, if. And then actually, we often call him P. Tony or Anto. I think he prefer to call him Anto. Formally, none. Okay. I think we are already now. Antonio, are you ready?
Yes, I am.
Okay. So let's start the talk.
Okay. So I'll start. Thanks everyone for coming, and I want to thank Campi for the invitation to give this seminar at IF. Yeah, it's any memories in Thailand, and my heart is still there. Okay, so let's start this talk today. Today I'm going to talk about, yes, minimal theories of gravity, mostly minimal theories of gravity, which nowadays are my main concern about modified gravity models. Yeah, so this is a work I've done with several collaborators. I hope I wrote all of them here: Andreas Doll, Keiichi Maeda, Shinji Mukoyama, and Masroor Pukilat. Masroor now is in Thailand, in Mahidol University, working with Burin. So, in a sense, okay, there is a. I am happy he is now in Thailand, actually. Okay, so, okay, let me start this this seminar with something that we all know, this thing of the presence of experimental puzzles in cosmology. So the first one I would mention, which is the most serious at the moment, is the fact that different experiments using the same model give different results for H naught, today's value of the Hubble parameter. Of course, that means, naively, that means that the model, either the experiments are wrong or the model I'm using is wrong. But if the experiments are wrong, not because they don't know how to do the experiment, but there could be unknown systematics going on. And on the other hand, if systematics are under control, then, and the experiments are fine, then we have to consider the case of changing the theory. And changing the theory would go into mainly two ways. One, add some matter field, or think about changing gravity. Yeah, changing gravity, for example, scalar tensor theory, although scalar tensor theory could be considered also adding some matter field, where this matter is actually the scalar field itself. Or, people have thought about massive gravity theories, where this one is it's like still working in the sense of not adding matter fields, but changing the fields we have. In particular, the graviton can become massive. But this also, in these theories, lead to extra degrees of freedom, which are tendentially a bit hard to control. But that's a very interesting attempt, which started many things, including my research in minimal theories of gravity. All right, so I would say that there could be a new cosmological tension. Indeed, it looks like the universe might be too thin, and by this, what I mean is that there have been studies which show that the universe doesn't clump as much as it should in Lambda-CDM or Planck. So if we put together Lambda-CDM and Planck, then we would have some prediction, for example, for the observable S8. On the other hand, if we look at the same observable by using large scale structures, here I put two experiment kits and DES, then we would get, again, assuming Lambda-CDM, but a different result for this observable. And the value of this observable at the moment is 3 sigma, about 3 sigma away from Lambda-CDM Planck. So again, maybe some unknown systematics should be taken into account. 3 sigmas are not, okay, maybe some people may not consider 3 sigma extremely, how can I say, compelling as the H0 tension, but still, the fact that we have now two tensions, different observables, could, it seems to me at least, could point to something non-trivial. So then, considering these tensions as real, so not affected by systematics, then point is, could both these cosmologies puzzles share a single fix? All right, so this is what I'm looking for, actually. This is what I would like to, at least to consider. Okay, so it looks like all these tensions point to problems inside the context of Lambda-CDM. But Lambda-CDM is essentially general relativity. So I want to say, okay, hold on a second. We know that GR works extremely well, at least if we don't consider those two puzzles. In fact, people found gravitational waves which are consistent with GR. And in particular, one single measurement told us that with a high value accuracy, at least for some, at least close to today, we know that the speed of gravitational waves is coincident with the speed of light. And this is not a trivial, this measurement is very deep. In fact, entire classes of scalar tensor theories are now ruled out because of that single measurement. Furthermore, GR holds true in the solar system. We don't have any measurement that goes against it, as far as I know. So then, if we look at all these things together in this, the last thing that you can see in these last slides, then you will say, is there any room for something else? I mean, is why would it change GR? GR works extremely well. So maybe this is pointing to the fact that the tension, maybe there should be some problem. Again, some systematics, because come on, I mean, GR works extremely well, except when we talk about cosmology. But okay, that's a possibility that should be taken always into account. However, there could be still possibilities to have modified gravity models which somehow work as GR when we look at scales which are not cosmological. So in particular, you could have infrared modifications. What I mean is modify gravity at scales which are cosmological. However, for scales much shorter than those, then this theory would look like, this new theory would look like GR. In particular, still we don't understand very well what dark matter is. We have not detected, I mean, we know the presence of dark matter, the gravitational presence of dark matter, but we have not found a particle which describes it yet. So, yeah, personally, I believe dark matter is a particle, but still, still again, something which is not needed in our experiments, in our, how can I say, in our accelerator experiments, because we have not found any evidence for it. Dark energy, again, yeah, dark energy could be a cosmological constant, but it doesn't need to be. And in fact, those tensions seems to point against a cosmological constant. But it may not be infrared modification of gravity. It could be some other particle. Again, another particle which is dark, in the sense no trace of it in our particle physics experiments so far. So there could be different phenomenological possibilities for this whatever modification of gravity. In particular, this modification could be responsible for the late time acceleration, clustering, flattening galaxy rotation curves, gravitational wave modified propagation on general backgrounds, and so forth and so on. But you see that all these things that I mentioned here can be testable. And therefore, this makes me very happy, because, if there is a modification of gravity which leads to phenomenological possibilities as those mentioned here, then those theories may be put to the test. Okay, now, on the other hand, when we introduce a new theory, I would personally thinking of setting some conditions for those new theories. In particular, 3 of them, I think, are good in order to introduce a new theory of gravity. The first one, I would call it a theoretical consistency property. In particular, what I mean in this case, to give an example, is that the theory should not have ghost instability. What I mean by ghost instability is modes which would make our vacuum unstable. Right, so that will, if this instability is not very long, does not have a very long time before the instability takes place, then this situation would really put serious problems into cosmology and particle physics. Now, on the other hand, so theoretical consistency, but also, of course, experimentally viable. What I mean is that the student should be able to reproduce all the known experiments. Right? Should pass all the known experiments. Those same experiments which are so successful in the context of general relativity. And finally, it should be predictable. What I mean is that we should be able to get predictions out of this theory. In particular, predictions are easy to find if, for example, there is no strong coupling, right? So perturbative approach can be performed on these theories. And finally, I would demand this theory to give nuclear predictions, right? For this theory, S8 is this, H0 is this other thing, actually. To make a theory which is, hides itself under GR is good, but at some point, this kind of hiding system breaks down because of the puzzles we have in cosmology. So the puzzles are the places where we would definitely look for phenomenology of this new modified gravity model. But let's see. So essentially, although so we had two puzzles and we had to try to solve them with the same theory. Now, I find myself thinking that H0 tension should be easier to solve rather than the S8 tension. The reason for that is H tension is a different evolution for H of Z. So I think that there should be some H of Z which fixes all the, I think there exists some H of Z which fixes all, we should fix all the experiments, and the H of Z should then tell us what kind of background dynamics we need for this IR modification of gravity. And it's conceivable to think of some potential for something that give rise to that dynamics for H of Z. Whereas S8 tension is a bit more complicated because we see less clumping. So less clumping can be thought of weaker gravity. So one way to see it, we have less matter, all right? But if we measure the matter we have, that means that with the same amount of matter, we see less clumping. We should think of having weaker gravity. So, all right, so that's typically difficult to reach with gravity in the context of standard theories, even in the context of modified gravity models. It's not so trivial to get it. Tendentially, what we need to change how dark matter behaves. And in a way that it, interacts in a weaker way than Lambda-CDM. All right. This may not be the only way, but it seems a reasonable way to get that. In particular, what we're going to talk today in this talk is three theories, mostly three theories, And they are all type 2 minimal modifications of gravity. I will tell you what I mean by that. And this theory is, it's VCDM, VCCDM, and extended minimal theory of massive gravity. Okay, I'm sorry, this is just the names. We will see later on what I mean by that. But for all these, some non-trivial framework is necessary to study them, even to introduce them. Right. So VCDM and VCCDM are similar to each other. And in particular, in the second one, we actually managed to include the dark sector in the context of type 2 minimal modified gravity theories. But extending minimal theory of massive gravity is interesting on its own because it leads to a non-zero mass to the gravity. All right, so let's consider this type 2 MMG theories. Okay, by minimal modified gravity theory, I mean a theory which has only 2 gravity degrees of freedom. GR, if you want, is one of them. What I mean here is that something which is beyond GR still has 2 degrees of freedom in the gravity sector. So, for example, Hondensky is not a minimal theory of gravity because Hondensky quintessence introduces an extra scalar degrees of freedom. All right. One example of this type 2 MMG, one of the first, as far as I know, is this MTMG, this minimal theory of massive gravity, which Shinji I introduced in 2016. Right. So in this, we introduce together with Andreas Doll and Shinji a model of MMG, which actually gives rise to an effective time-dependent cosmological constant. In particular, this theory does not introduce new degrees of freedom, so only tensor modes in the gravity sector. And it's possible to get very non-trivial dynamics for this, for H of Z, at the cost of, for free, in the sense we don't have to add new scalar degrees of freedom, new propagating scalar degrees of freedom, but we only add auxiliary fields. And in particular, because we don't add extra degrees of freedom, it's tendentially easy or easier than other theories to recover GR at short scales. Although all these things should be checked carefully, actually. And further, it's interesting that we can also extend the formalism introduced in this MMG to integrate dark matter. And this was done, for example, in this VCCDM. We are going to talk about both these two theories soon. In particular, let's discuss about this VCDM first. So the idea of VCDM is the original idea, the original framework was already done by Shinji and other collaborators, Katsuki Chung-shan, and I hope I'm not forgetting any of those. But yes, so the idea is rather simple at first, right? So the idea is, okay, let's start with the Hamiltonian of generativity in ADM variables, okay? Can you see my pointer?
I'm not see the pointer.
Can you see the pointer? No.
No.
My mouse. You can know.
I didn't see.
Okay. So as you see, the HGR is actually the Hamiltonian of general relativity. And wait a sec. Wait. Well, all right. So then, where H naught is the standard Hamiltonian constraint, and Hi is the momentum constraint, okay, in GR. Now, we can do a canonical transformation via using a functional f, which is defined here. And given f, then we have this canonical transformation. F is, so this is an example of canonical transformation where this phi and psi so far are just shortcuts for these scalars. All right, so once we have introduced this function, we can find the canonical transformation. So then what we're going to do is promote phi and psi to be 3D scalars by introducing inside the Hamiltonian Lagrange multipliers, which fix phi. You see, this is at this moment, this is just an equation, say what is phi, but we can state this one as an equation of motion imposed by Lagrange multiplier. Okay, so at the moment, we just made a canonical transformation from GR into itself. So still we have GR, maybe written in some weird way, but still it's GR. What we're going to do, which is non-trivial, is to put in the new frame a cosmological constant. Now, when we do this, it's clear that we have changed relativity because we start from, we should have changed a cosmological constant in the original frame to get still general relativity. But what we have done is actually something different because the new cosmological constant has not written in the terms of a previous cosmological constant in the old frame. So we have changed here, and when we do that, well, actually we had to add an extra constraint because the Hamiltonian constraint is not first class anymore, it's second class. We have to add an extra constraint. Otherwise, the number of degrees of freedom becomes unviable. All right, so essentially what we do, we add a cosmological constant in the new frame and add an extra constraint, and so that indeed then the new theory will still have 2 degrees of freedom. However, the theory is not general relativity anymore, actually. And the fact that the Hamiltonian constraint becomes a second class constraint means this is another way to say that 4D diffeo gets broken. So once we have the Hamiltonian, we can go to the Lagrangian, which I wrote explicitly here, just by using a standard Legendre transformation. And that's the Lagrangian we have. This part here seems to be trivial, except we have a potential here, which depends on phi, but phi is an auxiliary field. And then we have some parts here. You see, this is the extra constraint we had to introduce to make the theory consistent. As you see, this constraint sets phi to be at most a function of time. Having at most a function of time leads to this v of phi to be a function of time. This lambda is another auxiliary fields which could be in principle integrated out at once. Then we have standard model Lagrangian, which is coupled with a metric. Here you should say with a metric written in ADM. Okay, so yes, I should have mentioned that when we introduce this generating functional, f depends on two fields. So we may have derivative of this function with respect to phi and to psi. Indeed, those two first derivatives with respect to phi and psi correspond to two functions, f0 and f1. However, we may say that then, and because those in principle are free function, which depends on the original function we had, what we see is that actually they enter in the Lagrangian only through this combination. So we have two free functions that we can choose. As you can see, we can expand f in the last line in terms of an expansion in terms of psi, and this first capital F, its first derivative, if you want, is this f0, and f1 is the partial derivative of capital F with respect to psi. And these two, in this expansion, capital F and f1 are independent. Right, so however, they only enter in this kind of combination for V, the potential V. V is lambda tilde divided by that particular combination, and that is the only time where F0 and F1 appear in the Lagrangian. So essentially, VCDM has only one free function, which is this capital V, which is a function of this auxiliary field phi. All right, so we have this this free function of time because phi cannot depend on special variables. And in particular, what we're going to do now is a reconstructing thing. So what do we do? Okay, the second Friedmann equation leads to this time derivative where time is now the e-fold variables. Okay, this n is the log of a divided by 2 days a. And this derivative with respect to n is actually proportional to rho plus p. Rho plus p here is the total matter energy density. In principle, we can also add a curvature term, but it's not really necessary. Now, as you can see, so what happens is that if we choose, okay, in this particular time variable, if we choose h of n to be positive and rho plus p to be positive, then d phi over dn is positive, which means that we can invert. We can first solve, but we can also invert n as a function of phi. And because v, from the first Friedmann equation, v is actually phi squared divided by 2 plus rho, which is a function. Rho is matter fields, so we know how it depends on n because those are fluids which need to satisfy their own equations of motion, continuity equation. So we know how rho depends on the scale factor, which means we know how it depends on the e-fold variable. But then, using this relation, we know how rho depends on phi. And then we found that given an h, whatever h you like, we satisfy this condition, then we will know what is the potential which allows for the dynamics of h. Therefore, what we mean by this is that we have a theory which actually is what I call is an arena to attack h0 tension, which means that whatever hn you like, satisfying for this variable m to be positive, then if you assume there is a solution for H naught tension with our experiments given by some H of n, then, and that's a very reasonable assumption, right? Otherwise, either we had to say, no, H(n) is not always positive, okay, then we had to look for something else. Or the experiments are wrong. But if that's not the case, right, if the history of the universe inside the experimental thing we know allowed, it's consistent with H(n) to be positive, and the experiments are correct, then there should be existing some HOZ which fixes all the constraints, all the puzzles. Otherwise, some assumption gets wrong. So that indeed, then, so this is what we think this VCDM can be useful for. So any positive HOZ can be given. And then we have now an HOZ arena. Any HOZ which is positive, I should have said. Yeah, I mean, so it's possible to address H naught tension. This is what I strongly believe. In a sense, I think that it solves H naught tension. Because there should be an HOZ which fixes the job. In principle, we can think of wild possible modification of HOZ at any redshift. For this VCDM theory, we actually found a spherical symmetric black hole solution exists, and this solution allows for static solution, which are actually the same as general relativity. We also found static solution for compact objects, which are also general relativity solution. Yeah, so in particular, we also discussed the fact with Professor Maeda and Masroor and Shinji, the fact that there is also another theory, the Cascaton, which has also only 2 degrees of freedom. However, we show that VCDM is not Cascaton in the sense that it includes all Cascaton solutions, right? So Cascaton is a subset of VCDM. However, VCDM has also extra different solutions which are not inside the Cascaton theory. For example, VCDM has GR solutions whenever the phi field is purely constant in space and time, and the extrinsic curvature is constant in space and time. What it means is that GR solutions are also VCDM solutions in the context of constant mean curvature slicing. So indeed, the GR solution for the static solution we were talking before indeed satisfy the constraint that K is constant. It doesn't need to be 0, must be just constant. So what in GR, this is just a choice of slicing. There's nothing deep about it. As long as we can do that choice of slicing, then those solutions will also be VCDM solutions. Not always we can choose a slicing, but yeah. But at least there are many known examples for which constant K0 can be chosen. Okay. As an example of VCDM, we studied this H of Z. This is just toy model. And at early time, when Z goes to infinity, what happens is that this will give so this will give a -1 and 1 minus 1 is 0. So this one will go away. So we get only this one. But when Z equal to 0, you see when Z equal to 0, this guy here becomes 1, and we get another effective cosmological constant. So this model here just interpolates 2 different cosmological constants. So what we did with Masrur and Shinji, we actually studied the constraints from the data on the spin, and we see that we can ameliorate the H-naught tension, but things still can be improved by giving a different H of Z. But indeed, this how can I say, it seems a promising theory. Now, okay, so all right, so we have a theory which can solve H-naught tension. That's okay. But what about S8 tension? On the other hand, just doing one thing is not enough. Okay, and in particular, so what I want to do, what we are going to do now is to see how to extend VCDM in order to introduce dark matter. Okay, so so what we do, we are going to do the same thing. We are going to try to introduce dark matter inside the context of these MMG theories, but other particles in standard model actually will not be modified. So how do we do this? So the way we introduce this is Lagrangian for VCCDM. It's the first line in the Lagrangian is exactly the same as in VCDM. What changes is the dark matter Lagrangian, where dark matter Lagrangian feels a different G mu, which is not the standard G mu that other standard model fields feel. And this G effective is defined by an effective lapse, which, as you see, is this lapse for the G mu, but divided by F1, which is a function of this field phi, so which is a function of time. The effective shift does not change, but the effective 3D metric felt by dark matter is now divided by F0. As you see now, for the first time, F0 and F1 appears in different contexts inside the Lagrangian. So we can use both of them actually to try to fix H of Z and the G effective, the effective cosmological, effective gravitational constant felt by dark matter. And we can introduce a dark matter in terms of a fluid, for example, here, as you see, written down by a scalar field, but you can pick up your favorite dark matter Lagrange. So again, the standard model is coupled with the ADM metric in the usual way, but the dark matter is coupled with the G effective, which is actually given by this second case. And where F1 and F0 are function of phi, then it looks like we have interacting dark energy, dark matter. But remember, dark energy here has not does not add any new degrees of freedom. Phi is purely an auxiliary field. So, so what I did with Shinji is, okay, so let's try to reconstruct not only H, but also G effective. And as you can see here, in this particular example, this was very simple example. G effective is actually constant. We pick up F0 and F1 to be constant. But as you can see here, the clear point here is that baryons fields with baryons Gn, which is the standard Newtonian constant. So what happens? If we look into baryon physics, we should not see any deviation from general relativity. So which means that any experiment we do in the solar system by baryons, because we don't do experiment with dark matter, we will still see the standard gravitational constant. However, if we would be able to study interaction between dark matter fields, dark matter clouds, dark matter whatever, then we would see difference, actually, by this mu G effective. And of course, what happens is if you have less dark matter, because G effective divided by Gn could be less than 1, in turn, this would lead to less clumping in the dark matter, which would give, in turn, less clumps in also in the amount of baryon, baryon clumping, because baryon are also coupled with dark matter. So as you can see in this picture, we see the growth for the baryons, and you see that it is modified and reduced with respect to genetic. So indeed, VCDM is an interesting possibility. It gives interaction, does not touch baryon-baryon interaction, breaks the equivalence principle. Dark matter would behave different from baryons. And similar phenomenology of dark energy, dark matter interaction without extra degrees of freedom. And I think it's interesting to be studied in both linear and nonlinear scales. Now, in principle, we can also try to address H0S8 by extending minimal theories of massive gravity. So what is this? Maybe the tension can be solved by a massive gravity. However, when I say massive gravity, I mean a minimal theory, so only 2 physical degrees of freedom, because otherwise, typically, the scalar of this theory tendentially gives instability problem. We don't know for sure for everything, but there is known example. The RGT, for example, it has this feature. Okay, so what we look is something which has no BD ghost, no Higuchi ghost, and no linear ghost. Okay, so then we have to fix local Lorentz to realize ADM will bind the RGT, switch to Hamiltonian, add 2 additional constraints. It's going to be a bit complicated. Let me try to explain it later on, okay, a bit more in detail. But okay, suppose we make this theory. Actually, let me first discuss entomology, which is the simplest possible theory that we can get of it. And this theory is has 2 branches typically. All right, so this is true as exactly as in the RGT. We have 2 branches. So background exactly the RGT background. So the first one is when we want to set to 0 the first factor. Then we have a quadratic equation x, which can be solved, and then x is going to be constant. And this constant x leads to an effective cosmological constant at the level of the background in the Friedmann equation. The scalar vector perturbation are the same as Lambda-CDM, but the mass of the gravity waves become non-zero, in particular time-dependent. But we may have a normal branch, which means we fix to 0 in the constraint, background constraint, the second term. That typically leads to an x which is time-dependent. And therefore, in the Friedmann equation, we would have a time-dependent dark energy component. However, the dark energy does not introduce extra degrees of freedom, and the mass of the gravity is non-zero and in general time dependent. It's easy to see that we may recover GR because if the mass of the gravity is very light, we go to scales much smaller than 1 divided by m, then the effectively the graviton would become ultra-relativistic. Namely, we can discard the effect of a tiny mass for that. In fact, we tried it's possible to improve the fit of F sigma 8 by using this fact. This is true in the normal branch, where the scalar sector can get modified. ISW galaxy correlation also gets modification in the normal branch. We can calculate the observable, and we can see the prediction. And as you can see, there are some non-trivial things going on for this theta. Theta is the squared mass of the graviton with respect to h naught squared. So what happens is when theta is negative, so negative square mass, so the graviton becomes a tachyon, the observable seems to improve with respect to general relativity. But when we go to theta positive, which would be a good squared mass, actually things get very bad, or worse at least. So it looks like a tachyon graviton seems to be better shaped. What's the meaning of that, actually? In any case, yes, so the fact that we can see things get bad for positive theta, we can see them in the expression for G effective. As you can see, the denominator can become 0 for some values of theta. And that happens for positive theta. Y is a function of time, but you see that today y becomes equal to 1. So when y is equal to 1, we may have theta equal to 2, which makes the denominator vanish, and G effective becomes infinite. So something breaks down EFT theory, and the theory breaks, the description of this theory breaks down. So if we put studying what are the constraints on this theta, as you can see, Planck data really puts back theta into positive values, although still negative values are allowed, but it's the allowed parameter space is very small. Essentially what we are saying that h mu naught is almost equal to 0 because GR works in a sense. So it's not so ununderstandable that we get non-zero parameter space, which is very close to 0. Now, extending version of MTMG, what I'm going to talk in these remaining minutes is actually an extension of the previous theory. So the thing here is that we want, from the beginning, a theory which allows the square mass of the graviton to be non-negative, and G effective in absolute value to be bounded from above. Okay, so we don't want the denominator G effective to blow up in any case. So we also impose that dust behaves as usual. So in particular, to have a 0 speed of propagation at any redshift. And we also we impose a G effective over Gn goes to 1 at high redshift. So, okay, also we impose that the ISW effect has a finite contribution. By this, we mean that this capital sigma function you see, again, this should be bounded from above. All right, so then, however, we still want an h of z, which is different from Lambda-CDM in general. And in particular, we would like to have G effective less than G, and to implement weaker gravity. So if we have all these things allowed, at least the first 3 points, then we would have a bulletproof massive gravity theory. Then in terms of phenomenology, one still has to see whether these 3 things are enough to give a good fit to the data, but at least we would have a theory which can be trusted in all those redshifts. So here I put some reminders, but yeah, I mean, this mu square is actually a function of, okay, we'll see in a second what I mean by this. Now, let me introduce the Lagrangian of the theory. The Lagrangian of the theory is, don't get scared, it looks complicated. It is complicated, but it can be much worse if you think about it. So essentially what happens if we have some, the first line is kind of standard thing of general relativity. The second line is functions of two functions, which depends on things which is kk is, okay, if you know massive gravity, this is similar, but for the three-dimensional part of it. Kk gives inverse gamma tilde and gamma. So gamma tilde here, it's a fiducial metric, right, that can be given. And that, Gothic K stands for the inverse of that capital K. Then theta ij is defined that way. C zeta and C ij are functions, are tensors which are defined once you give those function f1, f2. The original MTMG actually corresponds to a particular choice for that f1, f2. So what's the phenomenology? So I give here a simple subclass of extended MTMG, probably the simplest possible choice we can make for f1, f2, are given in terms of 6 parameters. So C4, C squared, zeta 1, zeta 2 squared, zeta 3, which are real and positive, except for C4, which can also be negative. So in this case, the square mass of the graviton looks pretty simple. Huh? Now, it's not so complicated, this square mass, actually. And in particular, it's always non-negative, because R is also non-negative. It can be 0, but it cannot be negative, because also capital X is non-negative. Now, ISW effect, as you can see, it becomes, okay, some function here, which depends on G effective over Gn. As you notice, the denominator in the second term never vanishes. So that's exactly what we want. And G effective also has a denominator, which is delta in this, in the bottom right part, you see the delta, that's the denominator of G effective. Again, it's non-negative. So that's exactly what we want, is some G effective which does not blow up at any redshift. We cannot see easily, but G effective will go to Gn at early times for high redshift. All right, so the background dynamics is also given in terms of those quantities there. And then we expect some interesting phenomenology to appear. Now, I want to conclude. I have 1 minute to conclude, and I will do it. Okay, so we implement minimal theories to attack late-time puzzles. Minimal theories allow for wild modification of observables. And I discussed VCDM, BCCDM, and extended MTMG. Each of these theories has a different testable phenomenology. We need more data to decide whether they are sensible or not, whether they can really address all the tensions. On the other hand, we need to understand also the theory part of that. So thank you very much. I'm sorry, but my wife called right now. Probably
Okay.
she wanted to say, please stop your seminar. I don't know.
Okay, we have. Do you want to talk on? Are there any questions from the audience? P. Please use microphone.
Let me ask a few questions. Okay, when you apply the canonical transformation to the GR, then you obtain a new theory. So in vacuum, these two theories should be physically equivalent, right? Is it true?
Yeah, okay, so, okay, yes, when you make a canonical transformation,
Yes.
You are changing the variables to describe the same theory.
And
so the theories are equivalent. Indeed,
yes.
the theory are equivalent.
Yes. Okay. Okay. You can say.
No, the only thing is that we add a cosmological constant in the second frame, and that makes the theories not any longer equivalent. Because you see, so if we add, you see what is suppose I add. So we started with the general relativity without a cosmological constant, and then we transform, and then we add a cosmological constant in the new frame. And this new cosmological constant is not a cosmological constant. It's not a cosmological constant which was also present in the previous frame, which is transformed into a new cosmological constant. So it's like you see when, okay, in scalar tensor theories, right? So suppose you do a conformal transformation. You do a conformal transformation. You start from GI, you do a conformal transformation. Then you get a scalar tensor theory, which actually it's exactly the same theory as before, because what you have done is just changing your metric into a new metric. You just change the variables out of which you describe the theory. But then suppose in the new frame, I don't know, you add matter. And then then this will be, so what happens if you, and the matter field is the matter field written in the, how can I say, in the new frame, and you write it maybe minimally coupled to gravity. Now what happens when you do the inverse conformal transformation? The matter Lagrangian will have now some field phi into it, some conformal factor. And that is different from an original theory where you introduce in the original frame the matter field. So if you want matter fields for scalar tensor theories, determine the difference, say, in the Einstein frame or the Jordan frame. Okay. Now, something similar. So once you add matter, then you have different theories. So it's something exactly the same thing we did here. The cosmological constant corresponds to the simplest possible matter field you can add. And then the only non-trivial point here is that when we do this at the level of canonical transformation, then the Hamiltonian constraint becomes second class. And then in order to keep the theory consistent in terms of degrees of freedom, we had to add an extra constraint.
So, okay. My question is that if we add only cosmological constant, can we get different theory? You mean, according to your speech, you add both cosmological constant and matter, right? If we add only cosmological constant, we still get the same theory or different theory.
We get a different theory. If we add the cosmological constant after you do the canonical transformation, we get a different theory.
So is this implied that cosmological, when adding cosmological constant, symmetry of the theory change?
Which part of the theory?
Symmetry, for example.
Yeah. So yeah, indeed. Well, okay. So you add. Okay, so the first thing is to notice that you add, you are adding something that in the original frame is not a cosmological constant. Right, so a cosmological constant in the new frame does not necessarily mean a cosmological constant in the old frame. So because you did a particular canonical transformation, actually, then what happens is that in the yes, so you are adding something in the original frame, which is
I think about this because I read some paper, and they say that in order to construct the minimally modified theory of gravity, temporally for physics should be broken, something like that. So I ask you this question because because of
Yeah, for the diffio is broken. Okay, so for the diffio gets broken, right? And the reason, okay, one reason to see it is the Hamiltonian constraint is not any longer first class constraint. Okay, we'll have some non-trivial. So automatically, when you add the cosmological constant there, the Hamiltonian becomes second class, and then you have to add an extra constraint in order to make the theory, the degrees of freedom equal to 2. Now, the thing is that, okay, we broke the 4D field, and in particular, we have an auxiliary field, which is just a function of time. However, we can use a Stuhlkreber trick, if you want, to rewrite the same action in a covariant form. However, so then what happens is that the fact is that the scalar field, which is supposed to be time-like, okay, so we have, when we do the Stuhlkreber trick, we have to introduce a time-like scalar. So this time-like scalar introduces a frame.
Okay. The last question for you. You
So-
say that. Okay. The last question. You say that when you add matter in the MMG theory, you have to impose additional secondary class constraint, right? This because you have to fix some degree freedom in the theory when you add the matter in the MMG theory.
That's true.
My question is, can we use another choice of gate fixing other than you use in your work? Can we use another gate condition other than you use in your work?
Yes, the answer is yes. Yeah, the choice is right. So the choices of the constraints.
And what is the motivation for using the choice you use?
How can I say? The choice, the one we had, seems to be easy.
Oh, easy. Okay. Thank
Easy
you.
and practical. For example, yes, one constraints. Okay, so one of the constraints we have, right, sets okay. So one constraint we have is actually sets the auxiliary field to be only at most time dependent. And that was something that we kind of look for in terms of cosmology. Right? So we wanted something that if you introduce a function of this auxiliary field, that function can only become at most a function of time. So that function of time can in principle address H0 tension, for example. Now, so that was now, but there is another constraint with essentially sets that the trace of the canonical, of the momentum conjugate to the metric, the trace of pi aj, if you want, is a function of time. Now, this constraint here, again, is just a choice. Something different can be used. But again, it's somehow, in GR, this would look like a choice of slicing. And Yeah, so it's this thing essentially leads to the fact that we find these GR solutions which consistent with constant mean curvature slicing.
Okay.
So it doesn't need to be, these constraints do not need to be these ones.
Okay.
So yes, changing those constraints would change the theory, but keeping, of course, you have to choose two constraints which make sense, right? I mean, but once you do that, then you still have a theory with only 2 degrees of freedom. Phenomenology, you know, when we add the constraint, phenomenology can change a lot. In particular, phenomenology can kill solutions. Known solutions of which may be very useful in our everyday life, you see. So when we pick up constraints, we should pick up constraints which possibly do not kill known wanted solutions, but still introduce new phenomenology, you know, which can be testable.
Okay. Thank you so much, Daniel.
Thank you very much.
Are there other questions? Okay. One more
Okay.
question, Andrew.
Yes, please.
Maybe two. Okay, so when we want to add the matter field into the theory, right? We have to add the gate fixing term to make the theory still propagate. But right, for example, if I want to add some a dark energy or inflaton field, in total, the total degree of freedom in my model will be 2 or 3 in total with the gravity part and the matter part. So do you get my point?
Yeah, so, okay, so, all right. All right, so if you have so if I consider the theory that I was discussing now, this VCDM, this theory by itself only has 2 degrees of freedom in any possible context, in any possible background. So if you want to, right, so now if you want to generate perturbations from inflation, then you would need some some scale, I mean something that gives rise to that actually. So this one would only have tensor modes. Okay, this theory would have only tensor modes on any background, and in particular on freedom and method of Tensor Walker. So during inflation, if you add an inflaton, if you add a vector field, whatever you want to a curvaton, whatever you want to do to produce scalar perturbations, then yes. So then what you would you would add matter fields, and for example, if you add an inflaton, you would have one propagating degree of freedom in addition to the tensor modes. So yes, you can add matter fields as much as you want, and the number of degrees of freedom will be, in terms of number, the same as in general relativity when you add matter fields.
Okay, thank you.
Afterwards.
Okay, so another question is,
Yes.
Okay, for the MMG theory, we have to, before we add the matter field, we have to add the gate fixing terms, right? And I heard that, or maybe you mentioned in your presentation that some model of MMG theory equivalent to the Kakuton theory, Kakuton gravity, right?
Yes, yes.
Okay, so what if can we directly add the matter field in the Kakuton theory, or we have to like add the gate fixing term, like MMG theory? So
Hmm. Yes, so the Cascaton theory is a theory for which the scalar field is time-like. So yeah, you can pick up the frame on which phi is your time. Then yes, so in that case, actually, yes, if you add matter fields, you still have 2 degrees of freedom plus extra degrees of freedom, because in any case, we know that all the possible things. Okay, so what happens is that VCDM, it's really at least part of VCDM is exactly Cascaton. So Cascaton is not VCDM, but VCDM is Cascaton in the sense that there is a subset of VCDM for which the two theories completely agree with each other. And you can add matter fields in VCDM at any time, no matter what solutions you are considering. Therefore, adding matter in Cascaton is equivalent to adding matter in VCDM for those subsets. So adding matter in Cascaton, in VCDM is not a problem at all. Therefore, we conclude that adding matter in Cascaton is also not a problem at all.
yeah, thank you.
You're welcome.
Okay, I think it is time to thank Antonio again for very nice talk and very clear point in the answer. Thank you very much.
Thank you very much. And please enjoy Thai food for me.
Yes, we will go to Thai food now.
Okay, okay. Then I feel a bit envious, but yes. Sometimes I try to cook at home some green curry, but I still miss a lot Thai food. Actually. Sorry about talking about food, but but it's also dinner time for me, eh?
I think you should have a rest a little bit. You
Okay, I'll do it.
okay, thank you.
I think it's time to say goodbye, and
Okay.
then we will see you
Yeah.
again next time, and then we will have the colloquium for other months. If you want to join, you can join online.
Okay, very good.
Okay, thank you very much again, and then goodbye for everyone.
Thank you. Bye-bye. Thank you again.